Class, in this video we're going to be continuing our study on Pythagorean theorem. Previously we learned that the Pythagorean theorem is c squared equals a squared plus b squared as our formula, which means that the square of the hypotenuse equals the sum of the squares of the two legs. Now in the converse of the Pythagorean theorem, it states if the square of the lengths of one side of a triangle is equal to the sum of the square of the lengths of the other two sides, then the triangle is a right triangle. I know a lot of you are reading that and listening and thinking, what is different? Here, what we are doing is we are trying to prove that if I have a triangle, does it indeed form a right triangle? If you recall, we have done Pythagorean triplets, where if we were given the three lengths, 3, 4, and 5, and asked to determine if those segments were indeed Pythagorean triplets. This is very similar to the same process here. If I have the lengths of 3, 4, and 5, we want to determine if these lengths indeed form a right triangle. If the square of the lengths of one side of a triangle is equal, now what do we determine to be that one side? Very similar to when we were dealing with Pythagorean triplets. Whatever that longest side was, we let that be our C. We're going to do the same thing here. So, remember, we started the formula with C first. And in Pythagorean triplets, we had that placeholder, and then we wrote the rest of the formula. Very similar. We're wanting in this box to be an equal sign. If we can get an equal sign in this box, then that means we have a right triangle. These three segments form a right triangle. So let's see if indeed these three segments of the triangle form a right triangle. Notice that there is not that box in here to signify that. So we're going to let the longest side be our C, and we're going to determine if indeed we have a right triangle. 5 squared is 25, and using our placeholder, we have 9 plus 16. If we add, indeed 25 is equal to 25. Thus we can conclude that this is a right triangle. We now know, because of this, 25 is equal to 25, then this angle is a right angle indeed. That is the converse of the Pythagorean theorem. It's trying to determine if the three sides we are given do indeed form a right triangle. So let's look at one more example before we move any further, and I'm just going to erase. Let's just get rid of that stuff, and let's proceed with a different example. Here I'm going to draw the triangle, and our different segments are of, let's say, 6, and this side is 8, and let's say that this side is 11. We want to determine if this forms a right triangle. Well, notice that we're going to choose our longest side to be our C, using our formula, set it up. Now you don't have to use a box. Some of you may prefer to use a circle. That's perfectly all right. Whichever way is best for you. Some of you may even want to leave it blank. It doesn't matter to me. I don't know. I've just always used the box, so that's what I'm going to continue to do. So I'm going to plug in my values in the appropriate places. 11 being the longest one between 6, 8, and 11. And I'm going to try to determine if this does indeed form a right triangle. So multiplying out, we have 11 squared, that gives us 121. 6 squared is 36, and 8 squared is 64. Now we have to add 121. Let's see here, 36 and 64 is 100, and in this case our situation is not equal. So what can we conclude? This is not a right triangle. And going back to a previous lesson, we can also state that what? This is not a Pythagorean triplet. Now, what happens if we get this little situation of not equal to? We can actually determine what type of triangle this is. Remember, we can classify a triangle by the three ways of either being right, obtuse, or acute, correct? Well, that brings us to our two next theorems. So remember this problem. We're going to come back to it. if the square of the length of the longest side, notice they're using that longest side, like what we've always been doing, of a triangle is greater than. So if that longest side squared is greater than the sum of the squares of the two other sides, the triangle is obtuse. Notice how C is first. That's why I asked you to start getting used to that. Also, we have the next one. If the square of the length of the longest side of a triangle is less than, it's what it is. The triangle then is acute. Once again, C squared is first and gives us an acute triangle. So if we complete this and we get that not equal to portion, then we're able to determine if then, instead of the triangle not being a right triangle, well then we can determine is it acute or obtuse. And going back to the previous problem, let's scroll right back up and let's check that out. We want to determine if this triangle is indeed obtuse or acute. Now, what does it tell us? We have the problems or the values of 6, 8, and 11. So we're going to set that up. So, whoops, let's get rid of that. Let's get a pen. So we have C squared. We got our box. We have A squared plus B squared. I'm not going to work this out. Again, just going to plug in. We had 6 squared, 8 squared, and we ended up with 121 and 100. Now let's think, is 121 greater than or less than 100? Well, 121 is indeed greater than. So we have C squared is greater than A squared plus B squared. So that means that this triangle with the side lengths of 6, 8, and 11 is obtuse according to our theorem, because C squared is greater than. So I always like to look at it in this way. I always like to give us this example. If C squared is equal to A squared plus B squared, then we have a right triangle. If C squared is greater than A squared plus B squared, we have obtuse. And if C squared is less than A squared plus B squared, we have an acute triangle. So now some of the problems are not going to just be, hey, do you have a right triangle, yes or no? It may be, what type of triangle is this? Right, obtuse, or acute? So let's take that. And let's say we have the following three lengths. We have 3, 4, and 6. 3, 4, and 6 are our lengths. Now remember, we always want the longest side to be our C. So we're going to say 6 squared, 3 squared, plus 4 squared. And completing our math, we have 9, we have 16. Is 36 equal to, less than, or greater than 25? It is indeed greater than. So what does that mean? This triangle is obtuse. And let's look at one more example. Maybe this will hit home. What if all of the sides are the same side? Well, you're thinking, well, none of them's longer. So we get to choose. Do we want the first 5, second 5, or the third 5 to be our C? Well, it doesn't matter, I know. So we're going to say 5 squared, our little placeholder, 5 squared, and 5 squared. We know that 25 is going to be less than 50, without a doubt. So what does that mean? This is an acute triangle. Think about that. If a triangle where all 3 sides are the same, what type of triangle is that? It is equilateral. Now, we also know that if we have an equilateral triangle, it is also equal angular, and thus an equal angular triangle has all angles of 60 degrees. Are all 60-degree angles acute? Yes, they are. So it makes sense that a triangle with all the same side lengths is an acute triangle. So there we have it. We have the converse of the Pythagorean theorem, and also how to determine the different types of triangles, whether it's obtuse or acute, given the different side lengths.